Today we are talking about vertical stretch and reflect, or vertical stretch and shrink, technically. So today is February 10th. And what I'm going to do, just to sort of give you an idea, most of the things we have today, you can double check using your calculators. And I highly recommend that you do that, because half of your test you'll be able to use your calculator for, and the other half you will not. So at least you can guarantee yourself a good score on half of the questions, okay? As long as you know how to use your calculator, but you have to know how to use your calculator. So to start, last week we talked about translation, where we were sliding left, right, and up and down. The H value was the horizontal shift. When it was inside the function, it shifted left or right. What does the K value do? Up and down. That's the vertical shift. K is the vertical shift, and it goes up or down. So we had H's and K's all last week, and you guys did really, really well shifting things with H and K. And we're going to do that again today. But before we do any left and right, up or down shifting, we've got to worry about some other things. So first of all, let's look at our basic x squared function. What is the shape of y equals x squared? Parabola, yeah? It's a parabola. Oh, it's the parabola shape. Okay. So today we're doing a couple of things. And we know that the basic shape is a parabola, so we could graph that, y equals x squared, and I could graph it, and you can see that it's that basic shape. You can graph on that. Go check out a calculator. We just got 35 new calculators in. How about afternoons? And then, so today, what happens if I have a negative? And you can think about it like -1 times x squared. So here we have this negative out in front of the fraction, the function. What do you think is going to happen to our graph? It's going to point down. Yeah, it's going to flip. This is called what I call a reflection. And someone's music is really loud that I can hear right now.
Sorry, do you see any headphones?
Okay, and so you can see I could graph a negative x squared. Ooh, careful. All right, so there's that graph, and you can see that it got flipped upside down. I'd like to take a minute to sit right here. Sorry. Yeah, okay. All right. I loved Fresh Prince of Bel-Air when I was growing up. So good show. Good show. All right. So that negative is what I lovingly call a vertical reflection. And you can see that what's happening is we're taking these positive y values, and they're just flipping vertically, flipping over the x-axis. So those negatives cause our graph to flip upside down. Well, we're not only going to do that today, but what happens if I take my function, my x squared function, my parabola, and I multiply it by 3? What do you think is going to happen when I take that function and multiply it by 3? What do you think? Guesses? Whoops. Oh, that's interesting. All right. Let me erase that. I don't like how that looks. Okay, there it is. Y equals 3x squared. You guys can't see that. There it is. Okay. Any guesses? What do you think the 3 is going to do to our parabola? Make it fatter. You moved your hands horizontally. Okay. That's a good guess. Let's see. I don't know if you saw that, but Ryan moved his hands this way, so he thinks it's going to make it sort of a wider graph horizontally. So there's x squared. Oh, what did it do? It didn't get wider, did it? So let me talk about what's actually happening. We're taking our x squared graph, our parent graph, which we know went through negative 1, 1, 0, 0, and 1, 1. Those were the three main points for that x squared graph. Well, this 3 is what I would call on the outside of the function. And so because it's on the outside, anything on the outside is going to affect the y values. This is literally saying 3 times my y values, 3 times the function values or y values. So what it does is it says, it looks at this point, this basic point that we had at 1, 1, and it is literally going to take these y values and multiply them by 3. So this 1 is going to get multiplied by 3 and turn into a 3. Yes, the x didn't change, so it stays a 1, but the y gets multiplied by 3. Same thing over here. This original point was negative 1, 1, and we're going to multiply the y coordinate by 3. So it becomes negative 1, 3 right there. So it's actually, your hands, Ryan, moved horizontally, but what's happening is we're stretching vertically. It has the effect of making the graph look skinnier, but I call that just the Buddha belly effect. So I can everything to little babies. So because I got a lot of them, they I don't know how many of you have younger siblings or nieces or nephews or something like that. They go through the Buddha phase where like 6 to 9 months they're these little teeny chubby little babies, right? They get little wristy cuffs and ankle cuffs and little like thighs with rolls, like they're just chunksters, right? You got this Buddha baby envisioning in your head going on. And then all of a sudden they become a year old and all of a sudden they can walk and they just shoot up like 4 inches. They just grew taller. Their weight didn't change at all though. But just because they grew taller, they have the effect of looking skinnier now, okay? Even though their weight hasn't changed. That's what kids do. They pork up and then they thin out. That's what happens, okay? So that's what's happening here. This is called a vertical stretch because we are stretching taller, all right? A vertical stretch by a factor of 3. Factors, whenever we use the word factor, it just means multiply. And so we're literally multiplying the y values by 3. All right? So that's essentially what we're doing today. That is what we have to do first. Once we stretch or shrink things vertically, then we can do what we were doing last week, which is shifting left, right, up, and down. Okay? So our job is to make sure that we do any stretching first. All right. So really fast, ladies and gentlemen, I'd like you to remember what all the family shapes are. I'm going to pause this. I'm going to give you guys a second to remember what everything looks like. And I'm not going to go. Y equals the absolute value of x. What shape is it? V. Absolute value V. It has those 3 points.
Oh, that's absolute value.
Absolutely. You should know this. Absolute value V. This is y equals the square root of x. What shape is that? Swoop. Very good. 0, 0, 1, 1, and 4, 2 are those 3 points that it passes through. Good points to know. Y equals the cube root of x. What shape is that? The wave, the breaking wave. We've got our 3 points on the diagonal, 3 easy points. And this one is mostly side to side. Don't get crazy with curly lines. It's mostly horizontal, then up a little bit, and then horizontal, mostly. All right, nice and smooth. Y equals x squared. What shape is that? Parabola. It's those 3 points in a V again. but this shape is rounded like a U shape, parabola. And y equals x cubed, what shape is that? The slide, the wedgie water slide was what we talked about on Friday. Again, it's mostly vertical, jog to the right, and then mostly vertical again. The wedgie water slide where you better cross your legs because, man. All right, these are your basic parent graphs. You need to know the basic shapes of all of these. That is like, this is what, gentlemen, keep your hands to yourself.
I don't know why he's touching you.
Okay.
You saw that, right?
I did see that.
Yeah.
Okay.
No, can I move seats? Miss, can I move seats? He just touched me.
Okay. All right, moving on. There we go. Example 1, graph the core, then shift the function. On today's class practice, the way that I have it set up is I've prepped everything so that I start you off with our vertical stretch. You can see on this function, how many different transformations do we have? How many changes do we have to make? 3. Yeah, there's actually 3 changes. We got a 3 out in front, we got the 2 on the inside, and the 1 on the outside. So there's actually 3 transformations. And because there's so many, we have to be really careful about how we do them. So the order that you do these transformations matters a lot. And so just like order of operations, we do any multiplying and dividing first. So this says 3 times the absolute value. So first, I want to think about what's our core function? What's our parent function here? What shape is the basic graph? The V, yeah. Our basic graph is just absolute value of x, which is the V shape. So that's what I'm going to start with. I'm going to start with graphing that base or core function. And those 3 points that the V passes through are -1, 1, 0, 0, and 1, 1. And so this is our base function here, this absolute value V. But it's just for reference because we're going to do a little transformation here. The first thing I have to look at is this 3 times our function. Would you say that 3 is on the inside or the outside of the function? Outside. Yeah, it is on the outside. And because it's on the outside, anything on the outside is going to affect y values. Always, always, always. So this actually says we're going to do 3 times whatever these y values are. So if this is the point 1, 1, and I'm going to do 3 times the y value, what does this point turn into? 1, 3, yeah. Comes up here, 1, 3. And what it's doing is being multiplied by 3. We're taking the 1 and multiplying it by 3. It gets stretched taller to the 3. Here we have this point, -1, 1. And I want to multiply the y coordinate by 3. So what does it turn into? -1, 3. So all I'm doing is multiplying those y coordinates. I did the same thing with 0, 0. But if you multiply the y coordinate by 0, or not, dang it. I multiply the y coordinate by 3, what do you get? It stays 0, 0. So that one doesn't move, which is kind of nice. So this is our first little transformation, which represents 3 times the absolute value of x. On your homework today, I break that out. This is the first thing you have to do for me. It's just 3 times your base function every single time. And once you do that 3 times the base function, once you take care of multiplying, then we can do all of our sliding. So now I'm going to take my red function, and what does x minus 2 do to that function? Moves to the right 2 units, and the plus 1? Up 1. So I'm going to take my red function, and I'm going to go right 2 and up 1. Right 2, up 1. Right 2, up 1. Right 2, up 1. And so this is our actual function, y equals 3 times the absolute value of x minus 2 plus 1. So you sort of have to do it in steps. Deal with the number out in the very, very front, the multiplier there. That's going to multiply our y values, make things taller or shorter. And then you can slide everything. So now just looking at this green graph, domain refers to the x values, range refers to y values. So looking at our x-axis, how far to the left and how far to the right does the green graph go? Infinite, yeah. Negative infinity to positive infinity, left to right movement. The range is how low does it go and how high does it go? What's our lowest y value for the green graph? 1. 1 right there. And what's our highest y value? Infinity, yeah. So it goes from 1 to infinity. Bracket around the 1. All the way to infinity. All right, letter B. We have y equals 2 times the cube root of x plus 2. What's missing? The k, yeah. So what can we put on the outside here? 0, yeah. If you want to, you could put a 0 on there as a placeholder. So what I want to do is I want to know what's our basic graph here. What is our basic shape supposed to be? The wave. Y equals x cubed, or sorry, not x cubed, the cube root of x. The wave function, the breaking wave. So that is our first basic shape right here. I'm just going to do my 3 little dots. And this is the very basic graph. And the first thing I have to do is any multiplying that I have. So this is my first graph in red I'm going to do. With this 2 in front, this is saying 2 times my wave function. And 2 times my wave function is going to multiply my y coordinates by 2. 2 times the y value is what that means. So I'm going to just label these points my starting points here. So we have -1, 0, 0, and 1, 1. And I need to just take these points and multiply the y coordinate by 2. What does 1, 1 turn into? 1, 2, yeah. So the y, 1 times 2 is 2. The x stays the same. What about 0, 0? What happens to that? It stays 0, 0. 0 times 2 is still 0. And then -1, 1 is going to turn into -1, -2. And you can see what's happening. These points are being slid vertically. They're stretching vertically. So you can see they don't move left or right. They just go vertically higher or vertically lower. Okay. And so this is our stretched wave. So this is the graph y equals twice the wave graph. Y equals 2 times the cube root of x. Once you do your multiplying, now we can slide horizontally and vertically. So how are we going to slide our function now? Left 2, very good. This 2 is inside the function, inside with x. So it's moving in the left or right. This one is to the left. Up 0, So I'm just going to take my red graph and slide it left 2. 1, 2. 1, 2. 1, 2. And again, don't get all crazy with your lines. It's mostly horizontal. Domain and range. How far left and right does the green graph go? Infinite. Yeah, negative infinity to positive infinity. Forever left and forever to the right. How low and how high does it go? Infinite. Very good. Negative infinity to positive infinity. Low to high. Very good. Questions so far? All right. Are you not done yet? Do you need me to go back? For 1 second. Okay? Good. All right. Are you good now?
Yes,
They must have just been laughing at my joke. The big button. I don't know what's going on over there, but way too much fun. All right, we got y equals negative 1/2 times the quantity x plus 3 squared plus 4. So again, to start, I want to know my very, very, very most basic function. What is this based on? What is its basic shape? Parabola. Yeah, this is x being squared. Y equals x squared. Our basic parabola shape here is our base function, so that's where I'm going to start. And again, you definitely want to make your graphs large enough that you can actually see what's happening, so don't be shy. Like, I'm not making a huge graph, but it's definitely like about the same size as the space between the lines on your paper. All right, the basic 3 points for my parabola were negative 1, 1, 0, 0, and 1, 1. And I'm just going to write those down for reference. So we have those original points. Because I have something going on in front. So my basic graph here, first I have this thing, we're multiplying it by negative 1/2. So the first thing I have to graph is this multiplier, that negative 1/2. What's going to happen, do you think, with that negative 1/2? What does the negative do? It's flipping it, so it's going to flip it upside down. And what about the 1/2? Yeah, so again, this number out in front is outside the function. It's going to take our y values and multiply them by negative 1/2. So the negative is going to flip it, and the half is actually going to cut each of these points in half vertically. It's actually going to do what we call a compression. It makes those y values shrink, which has the effect of like making it fatten out, all right? You know, like when you take a ball of Play-Doh and smush it, it gets wider, right? That's what's happening here. So let's look at these y coordinates. Negative 1, 1, we're going to multiply by the negative 1/2. So what's 1 times negative 1/2? Not the x coordinate, but the y coordinate. So if I take my y coordinate and multiply it by negative 1/2, what do you get? Negative 1/2. 1 times negative 1/2 is negative 1/2. So we get the point negative 1, negative 1/2, which is right about here. It gets flipped upside down and then cut in half. 0, 0 stays the same. And again, this 0.11, the x stays the same. 1 times negative 1/2 becomes negative 1/2. So we have 1 negative 1/2. So it has the effect of making our parabola look a little bit wider. But really, it's just compressing those y values. Going back to Buddha baby size. Porking out. Okay. Which was me this weekend on Girl Scout cookies. Oh my Jesus. All right. So now that I dealt with that multiplying by the negative 1/2, I'm going to slide my function. How's it going to slide? Left 3 and up 4. So I'm going to count left 1, 2, 3, and up 1, 2, 3, and 4. And then I'm just going to go over 1/2. And that's our basic shape here. So there's our green graph, which is our total function here. Y equals negative 1/2 x plus 3 quantity squared plus 4. So looking at that green graph, what's the domain? How far left and how far right does it go? These arrows go down and out, so forever. Negative to positive infinity. The range, how low does it go and how high does it go? What's our lowest y value? Negative infinity, very good. What's our highest y value? 4. Right there. 4 is our highest y value, so it goes all the way up to 4. We've got a nice bracket there, parenthesis on the infinity. Oh, I'm hungry. All right, letter D is the last kind. This is a generic graph. I do want to show you before I do this one. You guys can write this down, but I'll show you. All of these first two that we did are regular functions that you can do in your calculator. So I'm just going to type it in, negative 1/2, quantity x plus 3 squared, and then plus the 4. So I basically just typed it in exactly how it appears. And then I can graph that. And there you go. There's a pretty good graph. And I can use trace. Trace is a great button. I can actually type in the x value of negative 3, and I get my output of 4 right at the top, which is really good. I can also type in negative 2, and it should give me 3.5, and it does. So all of these you can absolutely use your calculators for, and I encourage you to do that, to double check your graphs. But half of your test is going to be like this, where we give you a generic function. So this is a generic function that we need to transform. And what we're giving you are the generic ordered pairs for the original function. So what I'm going to do is I'm actually going to write these ordered pairs down, and we're going to see what happens to them. So you should make a list as well. My g of x function has points at negative 2, negative 3, negative 1, 2, 1, 2, and 2, 1. So these are the original points on the graph that they gave me. But now we've got to do some transformations. What's the first change I need to make? We got this negative 1/2 times my function. This is the very first thing we have to do. And it's literally negative 1/2 times those y values. And that's that first change. Negative 1/2 times the function. The functions are the y values. So for all of these y values, I want to multiply them by a negative 1/2. That negative 2 stays the same. What is negative 3 times negative 1/2? Or what's first of all, negative times negative is positive. And what's half of 3? 1.5. Yeah, 3 halves or 1.5. Half of 3. 1/2 times 3.